So today we're going to talk about Ohm's law, perhaps the most basic law in all of electronics. Now, Ohm's law you might know as V equals IR, but in electromagnetism it looks somewhat different. Let's have a look.
Alright, let's cue to a cheesy cutscene where I'm grabbing my favorite book on electromagnetism, Griffiths. There it is. Alright. Okay, so
Ohm's law.
Ohm's law. Gotta be in here somewhere. I'm sure it's going to tell us exactly that V is equal to IR. Of course it isn't. J equals sigma E. That apparently is Ohm's law.
Okay, well let's see what this actually is telling us. So we had in this fancy highbrow version of Ohm's law that something called J was proportional to the electric field. But let's take a further step back and ask, what is this J? This J is what's called the current density. So imagine we had a bunch of charges floating in three-dimensional space, and they're passing through some surface with area A. We can ask how much current or how much charge is flowing into that surface per unit time. And that is the current density. So for a very simple configuration where everything is moving in the same direction, say in the x direction, we're going to have that J is equal to the current per area in that direction. And that's the current density. So what that more modern, fancy, highbrow version of Ohm's law that we just saw was saying, it's saying that the current density I get is proportional to the force per charge. We've created some field, and the current density is proportional to how hard those charges are getting pushed. Now, we'll talk about whether or not that makes sense in a later lecture when we think about what materials are really doing. But let's take that at face value for now. So, it's proportional means there's a constant of proportionality, and the force per charge, the force is the Coulomb force, QE, per charge. That constant of proportionality is called the conductivity. We can also talk about the inverse of conductivity, and that's the resistivity. Now let's see if we can manipulate this a bit more to a more familiar form. Suppose for now that we just have a constant electric field. Not everywhere, but between 2 points, between point A and B. We have this constant electric field. There's a formula you might remember from first year or high school. I think when I learned it, it was called Ed's formula, that if you have a constant electric field between 2 points, the voltage is equal to Ed, the electric field, the magnitude of that electric field, times D, where D is the distance along that direction from A to B. So let's rewrite Ohm's law, this highbrow Ohm's law, in a way that talks about this situation here. I probably should have made these lowercase a's and b's, because we're going to use A for area, of course. So I have an area A, and we're forming a tube of length D, and we have some charge density flowing through it now. So rewriting our above equation in terms of known quantities, we have this. Everything's going to be moving in one direction, so I might as well drop the vector signs. And we'll have J, which is our current, divided by area, is equal to 1 over rho, that's our conductivity, times E. Now E is then V over D. Now let's just rearrange this so that voltage is on one side and current is on the other, and see what we see. V is equal to I, and let's collect all the other stuff. Some constant, rho times D over A. We'll call this quantity here, it's just a constant, we'll call it R for the resistance, giving us our famous V is equal to IR. So that's quite nice. We actually have Ohm's law here. And this is the form that we're actually used to. Okay, so that's Ohm's law. Let's move on and talk about this R here. R is the resistance. Now, for certain classes of materials, this constant of proportionality will not change as we change the voltage and the current. It'll be a constant. And then we have a direct proportionality between current and voltage. Not all materials have this, but some do. Let's try to sketch this. And materials that do have a constant slope, we better put labels on here. Now, often operationally what we're doing is we're adjusting the voltage and looking at the current. So I'll do it this way. In this case, the slope is the inverse of resistance. If that slope is constant, we have an ohmic material. We can test this experimentally. For example, a resistor will have this. There's many things that we're going to deal with in this course that are not ohmic. For example, we're going to see things in a couple weeks called diodes. And they have a current versus voltage curve that looks like this. Up here, the slope goes to infinity. That's 1 over R. So R is approximately 0. And here, it's very flat, approximately infinity. It goes to infinity. It seems weird to say approximately infinity, but you get the idea. This is what we call a diode. We'll have a curve like this. And it's not ohmic. In fact, anything, when you look carefully enough, is non-ohmic. There's always going to be some nonlinearity that creeps in. For example, a resistor that forms a light bulb, a resistive filament, will start off looking pretty ohmic, but as the temperature increases, it turns out the resistance, it won't go to 0, but the resistance will increase, so it'll taper off. And this would be a light bulb. And that's an example of a non-ohmic material. Okay, so we have things that are ohmic and things that aren't. Things that have a linear relationship with respect to voltage and current, and things that don't. Now, in nature, pretty much nothing is actually linear. Effectively, if things are linear enough, we call them ohmic. We can still define the resistance of something that is not ohmic. We can do it in a couple of ways, though. So we have our first definition. Our first definition of a resistance for, in this case, a conductor or an insulator, a geometric definition of resistance is what we had when we found this. It depends on the geometry of the substance and the material properties. Now, if rho is not constant or it behaves in a funny way, we can do an operational definition. We can merely define it as V over I, regardless of whether or not it's constant. We can define it at a particular voltage. We'll call this the operational definition. And we can define it at a particular voltage, and we can say generally it'll be a function of voltage or current. Let's say current of both. It will depend on that ratio in general. If it's constant, then it does not depend on that ratio and it's ohmic. This form is what is known as the static resistance. There's another type of resistance called the differential resistance. It also depends on the ratio in a way, but it's the instantaneous slope, i.e. the derivative of the voltage as a function of current. Now maybe you can see that for an ohmic material, the slope is constant. So the ratio is constant, and there's no difference between the static and the differential. But what's nice about this is it allows us to talk about the resistance of something that is not ohmic. For example, let's make a funny graph. Maybe we have a current versus voltage curve that looks something like this. So initially, let's say it's linear. And in this case, the static resistance is equal to the differential resistance. Here we can look, and let's put some numbers to this. Let's say this is 1, 2, 3. And similarly here, we'll have the static resistance. We have the static resistance, which is about, what's that going to be? about 3 volts over 2 amps. About 1.5 ohms. But the differential resistance is, we have to be a bit careful here. The slope is 0, so 1 over the slope is about infinite. So the static is very different than the differential resistance here. Even weirder, we have a region here, look at that region here, where the static, where you have a static resistance, some positive value for all these, but the differential value, the slope, is negative. So we have a differential resistance which is less than 0. We have a negative differential resistance. So that's pretty surprising, but it is a way that you can have a negative resistance. And this isn't science fiction. There are many devices that have a negative differential resistance. For example, fluorescent lighting, when you first turn it on, you have a high voltage which kickstarts some current. But as soon as current starts flowing, all of a sudden you have far less resistance along the path. And therefore, if you just took one of these light bulbs and flipped on the voltage and left it on, the thing would explode. For this reason, there's something called ballasts that are in these lights, and they repeatedly switch directions of the current or turn it on and off. In fact, some of them do so at 60 hertz, which is why you hear an annoying buzz in some old office buildings. But the newer ones are 50 kilohertz, which is more than twice the range of human hearing, so you don't hear that annoying buzz. I'm not sure if dogs hate being in those office buildings. But that is an example of a negative differential resistance. More voltage causes more current, causes more voltage, and you get a runaway effect. So that's how we can even talk about the resistance of things that aren't ohmic. Okay, the last thing we're going to talk about with Ohm's law is, well, we better talk about resistors a little bit. A resistor is simply a device with a well-defined resistance. And we make an abstract model of this. We draw it as a little squiggly line. But you can think of it as a tube with length d and area A, and R is going to be equal to rho times d over A. A resistor is just something with a well-defined resistance. And we can kind of get an intuition using this formula here about how a resistor should behave. We can see from this geometric formula that we have a longer distance, a longer resistor, we're going to have more or higher resistance. And we have a bigger area, we're going to have lower resistance. All right, so we can imagine that if we had a wire, we see that the length, this distance d here, is linear. If we double the length, we're going to double the resistance. And that means if we just string two resistors together, the resistances are just going to add. Now we can see this a couple of ways. First way, let's look at our geometric model. Suppose now for simplicity that they have the same area, just for simplicity. R1 then is equal to rho d1 over A. And we have R2 right next to it, which is going to be rho times d2 over the same area. We're keeping things simple and keeping the area the same. And this is going to be equivalent to some other R. We'll call it R, forget that that means static, we'll call it R sur, because this is what we call putting things in series. Is going to be equal to rho d1 plus d2 over A. But by simply expanding this, we see that R serial is equal to rho d1 over A plus rho d2 over A, right? And that was actually just R1 plus R2. And this is the law for a series addition of resistors. If we put two resistors end to end, it makes a new resistor, which is just the sum of the individual resistances. We're going to make a longer resistor. There's another way we can combine resistors in so-called parallel And intuitively, we can already see this is going to make the resistance lower because we have a larger area that we're putting the current through. So we can actually do this a couple ways as well. Let's do it a different way. The reason that we're not going to do it the same way, where we assume that we have the same area, same length, different areas but the same length, is that is going to be an assignment question in this course. So there's many ways of doing this. Let's actually have a look at an algebraic way of doing it. Now you can do the algebraic way for the previous method, but let's have a look at this. Suppose we're going to hook a voltage across here. We have VA and VB, and we might as well just call that voltage 0. So we have V volts across here, and we have some current flowing, and it's going to go into two different directions. It's going to get split up into I1 and I2. Watch the Kirchhoff video if you're not convinced of this, and that'll go back to I. Okay, so that's equivalent, when we kind of put a black box around this, to having a voltage across a new resistor. We'll call that RP for R parallel. We don't know what it is yet, and that's equivalent to just putting that voltage through there. And that same amount of current is going to run through it. We don't know how it's split up. So let's think about how we're going to solve this. Well, the trick is the voltage across R1 and R2 is the same. They have to drop the same voltage because they end up at the same place. V is 0 everywhere here, and V is whatever it was before all the way up here. So the voltage across R1 is the same as the voltage across R2, which is handy because then we can just write out an equation here that just basically says that. We have VR1 is equal to VR2, and that's also equal to VR parallel, whatever that VR parallel actually is. So let's write that out. We have I1 times R1 is equal to I2 times R2. The currents might be different. And we also have I1 R1 is equal to the total current, I1 plus I2 times our parallel resistor. All right. The total current is I1 plus I2. That's Kirchhoff's law for currents. Okay, so let's just eliminate I2 here. I'm going to move these equations over. They're creeping over to that side there. So this first equation, it just tells us that I2 is equal to the ratio of the resistances, R1 over R2 times I1. We can plug that into the second equation now, and let's see what we get. Okay, and notice that we have I1s everywhere now, so we can just get rid of the current. It's now an answer independent of the current. And let's apply a bit of foresight here. One of those magical things that people who teach do when they know the answer ahead of time and they know what they're supposed to get. We'll do one of those now. We'll divide both sides, or multiply both sides by, let's go R1 times RP. I think that'll get us what we want. And we will have RP, 1 over RP, is equal to, we'll get a cancellation of an RP here. We'll get 1 over R1 plus 1 over R2. Okay, and that's the so-called law of parallel addition of resistors. We can also do it in terms of the areas using the geometric formula, but that will be an exercise in the course. So that's it. There's another way of writing this, basically flipping everything around. We can put a common denominator and also write this as RP is equal to R1, R2 over R1 plus R2. Same thing, just rearranged. Now, that's pretty much it, but there's one thing I just wanted to say. If we have a big resistor and a little tiny resistor 2, say this is I don't know, 100 kilo ohms and the other one's 100 ohms. If we look at that, the way these add up, we're going to have R1, remember our big R1, over R1 plus basically 0, a little blip there, times R2. And this is going to be approximately equal to R2. So for parallel combinations, a few notes, the smaller resistor is what matters the most. The smaller resistor matters the most. And we always have a parallel resistance which is less than both resistors. The opposite is true for series. If we have one big resistor and one small resistor that's much, much less than R1, well, the total resistance is just going to be equal to R1 plus a tiny, tiny little blip. And that's approximately equal to R1. And if you want to see this slightly more formally, it's R1, 1 plus R2 over R1. And as that goes to 0, we basically have a vanishing contribution. So for series, it is the larger resistance that pulls all the weight. And that allows you to make some approximations in circuits. When you have a really big parallel resistance in parallel with a reasonable resistance, say a kilo ohm versus a mega ohm, you can ignore the mega ohm. If you have a mega ohm in series with a tiny 50 ohm output resistor, just ignore that 50 ohms. It's just a useful approximation. And that's it for Ohm's law, resistance, and resistors.